Why do other cryptocurrency applications view the network as a black box? They really do, because what cryptocurrencies and blockchain think the network is the peer-to-peer network. What you're going to hear throughout my talk is me referencing the peer-to-peer network versus the core network. To me, the core network are routers and switches with fiber and copper connecting them together. When you talk to blockchain people, they think the peer-to-peer network is, I'm a wallet, I send transactions through the blockchain, I broadcast them, which is an interesting verb. I broadcast them to a bunch of nodes that do all this interesting hashing and connect the blockchain together. So miners and wallets and daemons that all are part of this application level system are on the peer-to-peer network that rides on top of the core, capital I, internet. Why do other cryptocurrency applications care so much about security, but they don't consider the security of the core network? I mean, why crypto works, why we call it Bitcoin cryptocurrencies, crypto's in the name. It means it uses heavy cryptography, right? It's very important. Another theme in this presentation is the 3 S's: security, scalability, speed. We need these 3 S's everywhere in the stack. When you put a transaction in, you make the assumption as a user when you want to buy something with a cryptocurrency or even with a credit card. You assume that the underlying network that's making that transaction happen is secure. In fact, you don't really appreciate it. You make assumptions that it's secure, and you just trust something, that the infrastructure that does it. When you do a Google search, you know what's behind Google's data centers and the amount of scale they've put in to make your search work. Each keystroke is getting closer to a more specific search of material or information that you want. Scale is critical to make this work. Security alone is not enough. Scalability alone is not enough. And by the way, you don't want your transactions to take 3 minutes. You want them to be instantaneous. You walk into a coffee shop and you buy a coffee with a cryptocurrency. You want that transaction to happen in less than 5 seconds, or the people in line behind you are going to really be ticked off, right? So when I go buy coffee, I just double click here. I go like this and I move away. And people say, did you pay for that? And I said, yes, the system works. Isn't it amazing what's behind the scenes to make that simple task work? So security, scalability, and speed. Is the blockchain scalable? Oh boy. The blockchain is where the internet was in the late 80s. I see the same mistakes being happened that we made when we were building the original internet. So I think we need to bring the original designers of the internet and the designers of the blockchain together to show them what we learned, and maybe they could skip some of the mistakes we made so we can go directly to a scalable, secure, and speedy system. Well, if blockchain is so important for mankind, why don't we care about its performance at all the layers in the protocol stack? Not just the transaction layer. If blockchain is going to be ubiquitous, shouldn't it run over a scalable network? I mean, who's going to say no to that question? So intimacy between the application layer and the network layer is imperative. We have to start there. Anybody who doesn't do that, it's a non-starter, simply put. So layer intimacy, what does that mean? How are we going to achieve it? It's really pretty simple. When you boil things down, simplicity is going to offer you the most robustness in an architecture. And that's, I think, where we're going. That's where we're trying to go. And if things get complicated, it's you, the community, that has to tell us. We need feedback along the whole way, okay? What we want to do is we want to take the Tau architecture, the Nexus Tau architecture, and the Lisp overlay, and make them as close as they can to being as intimate as possible. We want it to be modular, we want it to be scalable, but we also want each of the 2 layers to be able to help each other. So what we're essentially doing is just taking the 2 layers, the application layer and the network layer, and making them more aware of each other, architecturally and implementation-wise. So what is the Lisp overlay? Before we talk about what the Lisp overlay is, you kind of have an idea from Victor's talk. Did a pretty good job of trying to present networking to people that may not have a lot of networking background because they work at the application layer, the financial layer, doesn't matter. But let's look at some various topologies. You'll find these topologies explained in the Tritium white paper. So the first topology we'll look at is the centralized topology. These black dots here are, let's call them crypto nodes. These are miners, wallets, whatever. And they're actually opening connections to all the other black nodes, okay, including that one that's in the middle, in the center. This topology is a hub and spoke topology, right? Hub and spoke topologies feel good. They feel good because you can manage them all in the center. Just think of if somebody wanted to find out what all those connection pairs were doing. By putting a tap in the middle of the nodes in the middle, you'd be able to find out all n-squared connections between them. That would make management very easy. It would also make a security attack very easy, okay? So the internet core or the network core would never be engineered this way, because if that was one router in the middle of the universe, wherever that is, and it goes down, then nobody can communicate with each other. This is a non-starter topology for the network core, but could be workable for a peer-to-peer network. But we don't suggest it. It's not robust enough. Well, what if we have a decentralized topology? Well, this picture here is the last picture, but we just distributed more in different spots. But you still see that those edge nodes still have connections to these mini hubs, right? So it's distributed, but we still have these single points of failure. An ISP network would look like this. Say we have a national network in France, like Orange, and these mini hubs here are different cities. This is how they would connect users. Those tail circuits would typically go to homes or cell phones, right? We're going to talk about multi-homing and how important it is, because we have multiple connections on this phone, multiple radios. Why don't we use all of them at one time? Why, in 2018, are humans turning on and off Wi-Fi wherever we go? Kind of an interesting point. Okay. So we want to do better than this decentralized network because it's decentralized but not enough. Then you go look at this distributed topology. This is a much better topology. Why is it? Well, it's more meshy. What does meshy mean? Well, the edge nodes have more than one link. In case they're directly connected links go down, they have some alternatives. So that you see in this diagram, the edge nodes have about 3 links to each other, and the nodes in the middle, which are usually core routers, have 5 links. And this is the way ISPs connect today. There's many exchange points all over the world that bring all the ISPs together. An internet service provider would be someone like an AT&T or a British Telecom or SoftBank or NTT or Comcast. These sort of providers. Not only mobile operators, but also pure internet service providers. Oops. So what about this topology, LISP overlay? Well, let's say those black nodes are cryptocurrency nodes, but let's say they're going to be Nexus nodes. And what's running in the Nexus nodes is LISP together. LISP and Nexus running together at the edge. And then you see this cloud. Well, as Victor showed you, these white boxes here are IP routers. That's the underlay. And the Nexus nodes are part of the LISP overlay. Okay. What LISP is doing is giving you a level of indirection. All computer science problems can be solved with one level of indirection, but just don't have too many of them or then it becomes inefficient. So basically, what LISP is doing is providing this addressing model and architecture where you can separate an address into identity and location, as Victor referred to. We call the identity in LISP EIDs. EIDs is just any IP address. The good thing is it can stay with you all the time and never changes. And the core network knows nothing about it. That's a feature, not a bug. We don't want the core network to know about it. We want to provide this abstraction so the core could scale. Okay? Now, how you get to an EID. So for example, I want to send a packet to Wendy. Wendy is the EID. It's the who I want to talk to. Once I know I want to talk to Wendy, where do I send packets to get to Wendy? Where is she located? She may have multiple connections into the internet core. That's what her routing locators are. And those are going to change. She's going to have multiple ones. She's going to detach and reattach from them. She's going to change from one to another as she roams. But Wendy is always Wendy. Thank God. Feature, not a bug. What is LISP? LISP is a locator ID separation protocol. Victor did an excellent job telling you where it came from and how it started. It's a pretty mature protocol. We've learned a lot, and I think it's very exciting for the crypto space. It's basically aimed, and the goal is to be a next generation internet architecture and set of protocols. Note that the EIDs are assigned to host nodes. Okay, when I referred to Wendy, it was a cell phone, it was a computer. It could actually be a service. Okay, and so those are assigned to hosts. They're IP addresses that DNS names would map to. Okay, and then routing locators are where those EIDs are attached to, and that's what the internet routing system connects to. So if Wendy has an LTE interface at AT&T, what happens is AT&T is giving her an address to send and receive packets. That's one of the RLOCs that binds to the EID Wendy. If she's also connected on Wi-Fi, then the DHCP server, the access point that's providing access here at the conference, is giving her an IP address also. So she's got an IP address on 2 radios. That's her RLOC set, her locator set. And I can actually send packets. If I want to send packets to Wendy, I can get it into either one of those locators. I can send them both at the same time, and there's increased bandwidth into Wendy. This is a good thing. So just remember, EIDs are part of the overlay, and the RLOCs are part of the underlay. And then we have this dynamic mapping that Victor referred to as the mapping system. The mapping system is cool. It provides all features that the internet currently doesn't have. Today, on the internet, and when we originally looked at the network, we said the internet is great because it could drop packets, and anybody could send packets to anybody in the world. This turns out to be a problem security-wise, because if I want to, I can actually DOS attack all your links at your house right now. Just because if I use up all the bandwidth, then anybody at your house can't use the network. The fact that I could reach everybody was wonderful. It's a great global community feeling to do that. But now we need some adult supervision in the network. So we need access control or admission control. I may want to talk to Wendy, but she doesn't want me to talk to her on weekends. So she doesn't register her RLOC set. But she wants Anastasia to talk to her on the weekends. So when Anastasia says, "Where is Wendy?" she gets Wendy's RLOC set. When Dino asks for Wendy, Dino doesn't get her RLOC set. So I can't send packets to Wendy. Anastasia can. Okay? So the benefits of LISP. Well, devices can move around and stay connected. Now, you guys, okay, how many people run the Nexus wallet? Let's see if I can see. Okay, so you see the number of connections when you bring up the debug console? And you see 8, 16, you know, when it's double digits, you're feeling pretty darn good, right? And you know that your blocks are being synchronized. So what happens is you close your laptop, you go from home to work, and you pick it up, and connections go to 0. Why did that happen? Well, your IP address changed. That's a bug. Why didn't those connections stay up? If the connection was made to Wendy and Anastasia's EID, and all the miners had connections, peer-to-peer network had connections to those EIDs, those connections would stay up. Do you realize how this is going to make the miners more efficient? The connections aren't going to go up and down all the time. Do you know what it takes to open up a TCP connection, a 3-way packet exchange? So you can close your laptop, bring it back up, and the connections stay up. And soon as you get the network connectivity to the RLOCs, you'll be syncing blocks that you didn't receive when your laptop was closed. This is a great feature for crypto in particular. And as I already said, devices can use all their network interfaces. So we'll get more bandwidth, we'll have resiliency to be able to load split packets across radios or across links. These miners are going to be in high-speed data centers with multiple 10 gig connections. They may be connected differently. We don't realize we're going to have satellite networking working, and we might have a connection to a cellular network, a fiber network, an optical connection to a satellite, or maybe a ring that's, I was just talking to Jim before the break, and he said, you know, we could consider doing an optical ring around the satellites up in low Earth orbit. So there's going to be all these different connections, and we have to be able to be resilient. Each of those connections have RLOCs, and you map EIDs to those sets of RLOCs. And when I send a packet to where Wendy is, it's taking the shortest path in the underlying core network from me to her. It doesn't hairpin through a central exchange. If I want to if I want to open up a connection today to Wendy, and depending on the application we're using, we're going to hairpin our traffics to Google, to Facebook, right? That sounds pretty centralized. We should all be able to communicate right now in this room using Wi-Fi or even Bluetooth, because we all have network connections and we should be able to talk independently. That's the kind of decentralized internet system we want to build, right? If there's a disaster, a catastrophic hurricane or whatever, and people need to talk to each other and they don't have a connection to the internet, but they still have networking on their phones, they should be able to talk to each other. This is what the original designers of the internet wanted. They wanted free access for all. I mean, the internet is sometimes more important than electricity. Unfortunately, we can't run without it. For a while, we can. So devices can only talk to each other when authenticated. You'll see some, in our demos, you'll see some interesting things on how we can authenticate both at the blockchain level as well as down at the network level. The device data on the network remains confidential. Victor showed you that all packets that are encapsulated from my locator to Wendy's locator are all encrypted. They're encrypted by doing Diffie-Hellman between the two LISP nodes at the end. Nobody in the middle is involved in this. I could change my key every 1 second, and then I can be re-encrypting with a different key as I'm sending packets to Wendy. So nobody can collect all the packets in our conversation and assume that there's one key. They have no idea which key I changed for which set of packets. So it's pretty darn secure, okay? And while we're doing all this, we're adding scalability. Wendy, Dino, and Anastasia, these are 3 EIDs. An AT&T router doesn't know anything about it, and shouldn't, because we are 3 individuals out of 6 billion people. Can the underlying internet core store 6 billion pieces of state? We know we're going to have tens or hundreds of billions of addresses once IoT comes, and it's coming fast. So let's explain our architecture. Okay, so this is the OSI reference model that was built by ISO in the early 80s. It was a 7-layer architecture that most hosts would implement. When people refer to the protocol stack, this is what they're talking about. Okay, so the physical layer basically tells you if you're using copper, fiber, RF. The data link is framing and making frames that go over these links secure. The network layer are what routers run at. And when we say you have an IP address, it's routers that operate at the network layer that route based on IP address. Transport layer provides reliability for these packets that go over the network. And session layer is another form that you can add security and data representation, and then applications run at the application layer. So we're going to show you how where LISP fits into this OSI reference structure and where the Nexus TAO is going to as well. So LISP is basically a subcomponent inside the IP layer at the network layer. And it basically receives packets from the transport layer when packets are being originated. And then it assumes EIDs, and then it maps it to RLOCs. And then when it sends packets out Ethernet or RF or whatever, then it basically puts another header on, like Victor was showing you, saying that the outer header are RLOCs, the inner header are EIDs, and that's what goes through the network down to the data link. Where Nexus resides in the OSI architecture stack is up there at the session, presentation, and application layers. This is where the Nexus daemon, the miners, the wallets all run. And those guys will originate packets with a source address of an EID talking to another EID. And that means this is where the Nexus node will be part of the overlay. So when LISP is co-located, and that's our plan, our design decision we made was to co-locate LISP with Nexus. We are basically making the Nexus nodes part of the overlay. Now, this intimacy is really important, because now that I'm a miner and Anastasia's a wallet and she wants to send a transaction to me, she can decide out of those connections who to send it to. She may want to send it to Victor, who is the first top miner or something like that. But she realizes that if she asks LISP where the locators are for Victor, and they have high RTTs, and there's some queuing delay or packet loss in the network, she could say, I'm going to go now look at Wendy as a miner. I'm going to go look at her RLOCs. Well, if her RLOCs are getting some good performance, I'm going to now send the transaction to Wendy instead of Victor. Now Nexus can make intelligent decisions how to broadcast through the network based on real live data, telemetry data. And we're co-authoring, Colin and I are co-authoring a LISP telemetry spec to tell people how to implement this in routers. And we have a software implementation of it too. And if you want to know more details about that, I just wrote an application that actually looks in the map cache, retrieves all the RLOCs, gets all the RTT and hop count information that LISP computes, and then does a trace route where you know each underlay hop to get to the RLOC, and then you can find the RTTs of every hop. I mean, the thing is Nexus can say, I don't want my packets to go through AT&T because today they seem very slow, but Verizon seems much better. So all the miners that are in Verizon or off Verizon, I'm going to send my transactions that way. That's pretty darn good. Agree? Disagree? Okay, agree. Okay, good. So let's look at the Nexus module at the application layer. Colin did a good job of being a generalist as much as he can until when you code you have to make decisions. But it turns out if a Nexus application sends to a non-EID, in other words, an existing system, it will just use a regular IP address. And that's what you see on the right-hand side there. If he just sends to a miner today, he's actually sourcing from an address that is routable by the underlying internet. Okay. But if Colin decided to send a packet to an EID based on going to an EID, and we carve out this 240 space in IPv4 to say we're going to use them as EIDs, then we can decide what the source is. So just by Colin selecting who he's going to open connections to, we can say that the source is going to be an EID, and therefore it uses the overlay. What I'm trying to say here is that Nexus can work with or without an overlay at the same time. This is an incremental deployment of LISP. It's not a turnkey where everybody has to change. We can trickle this out very slowly among the network and make it work. The people that want the benefits of the overlay source packets from EIDs. The people that don't just use their regular addresses as they work today. But you can put your system anywhere. You put it at home behind a NAT device, it will just work. If you put it up in space, it will just work. This is what's important. So EIDs are mappable addresses. Remember that. They have to map to where you want to send packets for that, who you want to talk to. And the RLOC addresses are the routable addresses in the underlying core. Okay, so what we did is we built the Nexus software stack. And we said we're going to build an architecture and a system that's going to be made up of layers. And you see on the left-hand side is the OSI reference model. And you see on the right side is the Nexus software stack that we documented in the Tritium white paper. And as you can see that all the 4 layers, we just call them network services. And the network services includes LISP at the network layer. Okay, so when Nexus decides to send packets, I'm going to work from bottom up now and show you what LLP is. And of course, Colin's going to talk more about this. We're focusing, my presentation is supposed to focus on the lower layers, and he's going to talk about all the great features that we put into Tritium and what will be coming in Tau. Oh, you guys want to know when Tritium is going to be released? Yeah. Soon. Okay, so LLP is basically the messaging that is a transaction, a get block, those sorts of things that you all know and love from Bitcoin. And you're going to see a lot of improvements in that. And the ledger is obviously the blockchain or the DLT. And then we've introduced object registers and state registers to hold values and tokens and sort. I'm just going to go through this briefly because Colin will deep dive all this stuff. But what's important is those APIs, we're going to try to write those APIs at Nexus so customers can use it. But we want customers also to write APIs. And those APIs could interface directly down into the operation layer, or they can go just straight to the ledger if they don't want to use the operation and register layers. And so we treat it now that as, from an architectural perspective, that the customer service DMARC is going to be that API layer. But we want everybody to write APIs. Okay, the demo. So I'm going to show you 3 different demos that are going to illustrate some different things. And it's a live demo, and hopefully everything's running and the network is up. Hey, the network's running much better than the microphone, so that's a good news. Okay, so the first demo, what I'm going to show is we have this server out in a data center in Kansas City, and we have a bunch of Docker containers that are running. And as you can see there, each line there is a different container. What the container is it's showing you a Nexus node running Lisp. They're being co-located. All these nodes are running Nexus 246. And the reason we didn't upgrade is because we wanted to show you guys we have a pretty good uptime here. If you could, oh, I shouldn't show you here because these slides were done a month ago. But so when the slides were done, we had an uptime of 9 days, right? But when I show you the live screen, I'll show you the real uptimes. So what the first demo is going to do is show you those top 10 containers up there running. So Nexus is running, it's opening up n-squared connections to each other. And I'm going to show you some ping tests, okay? What I'm going to do is I'm going to do some unicast pings. A unicast ping means I'm pinging Anastasia, I'm sending her a single packet, she replies with a packet back that tells me that the forward direction to her and the reverse direction is up and operational. Then we're going to show some multicast. We have 3 multicast groups that are being joined right now, okay? 224.111 is one that's going to be realized by underlay multicast, like Victor was telling you. That means the underlay is supporting multicast. But the other 2 groups, 246 and 357, we're saying is not going to be supported by underlay. So we're going to do head-end replication. So the way we made it work was 246, our XTR is 246. Those are the only 3 nodes that are joined to that multicast group. And then the odd ones, 357, are joined to 224, 357. Okay. Now, when you see 224, think that's a multicast address. When you see 240, we've decided that that's going to be an EID. So I'll show you those specifically. Okay. So let's go to that demo right now. Okay. So the way to make a demo successful is to have it run before you start. Okay. So what's going on here is the full unicast ping mesh. You see these 240 addresses here? So this ping is being started by XTR1, and it's going to 1, 2, 3, 4, 5 all the way to 10, and then it starts over again. And I have it in a loop running. Okay. All this is telling you is that don't worry about the invalid argument thing. This is a memory thing. This is not a bug from me or Colin, right? It's stuff we have to live with, right? Okay, so this is the ping that's going. Let's do a multicast thing. Okay. So now what I'm going to do is I'm going to run this, I have this ping multicast script getting ready to go here. And I'm just going to paste it in here. And you see that the first thing that this XTR1 is sending to is 246. Okay, so what does this mean? A single packet is being sent to a multicast group, 224.246. The underlay is mapping that to 239.111. That's the multicast group on the underlay that's being sent. So what do we see that's going on here? Well, when we send to, okay, this 111 means all 10 of them are joined. So you see all 10 of them are sending replies. I'm sending 1 ping to the group, and 10 replies are coming back. Okay? Oh, let me run it again so we can see it better. The first one was being sent to, okay, this one, 246, you see only 246 is replying. Now we're doing 357, you see 357, 3, 5, and 7 replying. Okay? So a lot's going on behind the scenes, but this is multicast in action. And now that we have this type of capability of doing multicast, Colin's going to tell you how we're going to use it for perhaps L1 locking groups, L2 miners, L3 and Obsidian, okay? There's a lot of things that we could do with this, okay? So that's XTR1. Let me go to the next demo. Oops. Okay, so when we looked at the last demo, we said we had 10 XTRs, and then how did you find out what their EID to locator mappings were? Well, they were registering it to the mapping system. Now, the mapping system is a distributed and arguably decentralized system, very much like the domain name system that we use to resolve our DNS names. But what we did here is we actually ran this other container called MRMS. It stands for Map Resolver Map Server. So map requests can go to it and they get resolved. The basic protocol machinery, control plane machinery that Victor was showing you. What we're going to show you in the second demo is we're going to bring up another 10 containers, and they're going to be running Decent. Decent was the decentralized mapping system. Colin and I put in an internet draft in March into the IETF, looking at ways of not having a central body do the mapping system. And what that means is that all the XTRs, all the Nexus nodes running Lisp, are the mapping system for each other. Very much like a peer-to-peer network. Wow, we learned something. The networking guys, the old guys, learned something from the crypto guys. This is goodness. Okay, so what's happening is we're sharing this information from the application layer to the network layer. This is wonderful. This is community. This is awesome, right? Okay, so what are we going to do here? We're going to do some mesh pings, and we're just going to see that it works. But what I'm going to do is I'm going to actually web interface into one of the XTRs, and I'm going to show you what the map cache looks like to prove to you, okay? Someone's trying to call me. Okay? To prove to you that we're actually having n-squared connectivity among the 10, and that the mapping system is on each one of them, because now they're acting each as map servers. I'm going to connect to let's run oops, I forgot to use my keyword. Okay, so one is sending to himself, and he got a response from himself. That's good. If you can't talk to yourself, you can't talk to anybody else, I guess, right? One is sending to 2, sending to 3. So it's doing the same thing it did last time, but why is it different? Okay, so this is Decent XTR1, and we're going to show you the map cache. What is the map cache? Map cache is a routing table or a data structure where when I said I wanted to send packets to Wendy and I have to know where Wendy is, well, if you look up here, when 1 wants to send a packet to 2, look at the very first line, you see that there's 2 routing locators. That means this guy's multi-homed. That 20028 address could be a connection to AT&T. And 172.17.029 could be a connection on your Wi-Fi. And you see that what we're doing is we're actually testing both our looks to see if they're reachable or unreachable. Right now, we believe they're unreachable for 10 seconds and 20 seconds. If you see these green numbers, that means, if you see a dark green number, it means a packet was sent to it in the last second. If you see a light green, it means a packet was sent to it in the last minute. That means we're moving packets through this thing, and we're moving them to all these places, okay? You don't believe me? That's Nexus running. That's Lisp running. I'm showing the processes on Linux that are running. This is showing you a get info, and the get info says that we go down to the number of connections, 9 connections, right down here. Okay? Don't worry about there's no money in here. I don't do this for money. I do it for connectivity. Okay, so that's the map cache. But what's interesting here is we didn't have to go to the mapping system. This guy, when he wanted to look up 2, he sent a map request to himself. Well, that means he has to be a map server. Well, that's what he is. He's a map server. And he has mappings from all the different EIDs. They all do. And therefore, it's being kind of pushed. Well, how's it being pushed? We use overlay multicast. We use the techniques that we build. So for instance, when we were going to 2, let's go down here and just click it. You can see that these 2 locators right here in blue are the ones that you saw in the map cache. So we're looking at ways of doing a pull-based distributed, decentralized mapping system as well as a push base. Our first version is a push base, but we're looking at bringing some interesting concepts from peer-to-peer networking at the application level at this level as well. Okay? Clear? Everybody's glazing over? Don't say what LISP stands for or they'll freak out. Okay, the last demo. Okay, the last demo is cool. We showed you, if you looked at all the addresses and you saw dots in them, that means they're IPv4. The capital I internet pretty much runs on IPv4. But we're running out of addresses. There's only 2 to the 32 addresses. It's not enough. So what we want to do is we want to be able to run over IPv6. This is a simple thing to do. And what we decided to do was bring up 25 containers, each running crypto EIDs. So what is a crypto EID? A crypto EID is an IPv6 address, and what we've decided to do is take 120 bits of that address and make it a hash of a public key. Okay? Now think of this. We have private and public key pairs at the network layer. We have many public and private key pairs at the application nexus level. How can we use them together to make them more secure for each other? Should we share them? Should we keep them separate? These are all architectural decisions we're going through right now. And Colin will have some comments about how crypto EIDs could be used in the blockchain. Okay, so let's show you how that works. Now what's interesting, these crypto EIDs are opaque addresses, right? I just can't say, I want to send a packet to, 128 bits because I don't know where it is. So what I had to do is I had to write a script to look up in the mapping system the crypto EIDs that were being registered. Because if I took all the containers down and brought them back up, there'd be a whole new set of crypto EIDs that would come up. Okay? So let me go into, I can show you uptimes. Uptimes are important, right? Okay, so this is I'm showing you all the Docker containers that are running on there. And you can see that we've been running this code for a couple months now. So do you guys want to know when Tritium's going to be released? Soon. Okay, so let's go into crypto XTR1. Okay, I'm there, and now I'm going to start a script. And the script is here. So I'm fetching the registered crypto IDs from the mapping system, and I didn't find them. Of course not. Don't forget the internet scales because it drops packets. Okay, there we go. So those were all the EIDs that we found in the mapping system. Those are 25 IPv6 addresses. And FD is the prefix, and the other 128 bits is a hash of the public key. And now I'm doing an n-squared ping across all of them. Okay. And so I'll show you the map cache, and then that'll conclude the demo. Okay, so of course the Nexus nodes are still sending packets and have TCP connections to all these 240 addresses, IPv4 EIDs. And then if you come down here the ping n-squared mesh is happening, and you see that we have these IPv6 EIDs mapping to IPv4 RLOADs, and we see packets moving. That means you guys can run secure IPv6 at your house, and you don't have to call up Comcast or AT&T because you're running an overlay, and LISP is an incrementally deployable solution. We can now address billions and billions more particles in the universe. How many only Colin knows the answer to this question. How many particles are in the universe? 2 to 123 is the maximum. That's the energy in the universe over the last billion years. Okay. Until he figures it out, right? Anyways. Okay. Thanks for that. Okay, so those are the demos. Colin's now going to show you, when he comes up, he'll show you a really cool demo at the application layer as well as the wallet. But if you want more info about this stuff, it's obviously completely open. We always want that to happen. NexusEarth.com, Lispers.net is my website that has some pointers to presentations on Lisp over the last 10 years. Use the normal support channels. Anastasia never sleeps, so she'll always answer you. And then I would like to say that, you know, I got involved in all this exactly 1 year ago. It was at the Nexus conference in Aspen where I was asked to speak, and then I went to that great lunchtime conversation that Colin had. And I just basically raised my hand and asked a question. I met him at the conference, and I just thought, oh gosh. I explained Lisp to this guy. In basically 15 minutes, he got it, and he was already building features in Nexus that I couldn't understand about Lisp. So that's Colin, right? Everybody knows that. But you know, you don't have to be a coder or a geek or a technical guy or gal to be able to get involved in this stuff, and that's why we created these working groups. Everybody has a skill, and maybe you'll be up here next year doing something. So don't feel like if you're not technical or you don't understand it, that it should stop you from doing things. We need people to educate. We need people to document. We need people to test. We need people to make money with miners. All this kind of stuff is all useful. We all need each other to make this a global success. So we put these working group together, and we want you to come to it. There's sign-up sheets over in the, where are they at? At the registration desk, there's sign-up sheets. And we're going to start off with the DAC working group, where Jules is going to lead that. And the DAC and the functionality working groups are going to be higher level. So if you have your use cases, or do you say, there's this problem in the world, can the blockchain solve it? You go to the functionality working group. If you want to be more about people and community, go to the DAC working group. Then if you want to be a little bit more technical, we have the Arch working group. That's going to be a working group that's going to look at all the layers. You see what we've done is we've taken the layers here and we divided it up into manageable portions. And so we have an app working group at the top of the stack, a contract working group. Dylan's going to do the app working group. The contract working group, Dan's going to lead. The ledger working group, the contract, who's doing the contract? Colin, of course. The ledger working group is going to be done by Dan. I'm going to lead the network working group, and Colin will do the Arch working group. So it's just going to be an open discussion forum. We want to be able to discuss things. We're going to build a real-time agenda, and we're going to ask people to write simple documents to express what they want and help. We want to build this stuff together. So please sign up for the working groups. The whole Nexus team is really looking forward to this. Anyways, that's it.
Come see what we're doing at nexusearth.com.